Hello and welcome. This is Rick. Today we're going to be talking about logarithms. Have a little bit of an introduction to those. The striking young man, I suppose he's an older man here, on the screen you see is John Napier. He's a Scottish mathematician, theologian, necromancer, alchemist. Those last two are only by rumor. Necromancer is somebody who talks to dead people, their spirits, I suppose I should say. Alchemists, they were interested in turning, common materials into silver and gold. They were also interested in coming up with substances that would generate the elixir of eternal youth. Think Harry Potter and the Sorcerer's Stone or Philosopher's Stone, depending on which edition you read. So here we have John Napier. He's a 16th, 17th century mathematician, theologian. As far as theology goes, he was famous for predicting the end of the world would be about either 1688 or 1700, based on his calculations from the book of Revelation. He joins a long list of other folks who have predicted the end of the world, if you're listening to this unsuccessfully. His real claim to fame in mathematics was he published 57 pages plus a 90-page addendum of tables called the Malefici Logarithmorium Canonis Descriptio. My apologies to Marcus for however I butchered the Latin on that one. English translation is the description of the wonderful canon of logarithms. These were a pretty amazing invention for the time because what it allowed was to do calculations on large numbers, numbers with complex decimals, some really stuff that was hard to do by hand at the time. He came up with a method along with his tables that made this much easier, that really advanced a lot of the work we now know in astronomy, physics, and dynamics. Canon, essentially, since he invented it, he did the first big write-up on it. Canon just means the official law, the official rule. So he invented this. Now, why is this important? Well, logarithms give us a way to multiply, essentially using principles of addition, which led to the invention of the slide rule. Slide rule is quite the amazing instrument. Oh, let me go back. Here's a slide rule right here. Okay. The slide rule was a pretty amazing calculator for its time. I'm part of the last generation of American high school students that learned how to use a slide rule. I was going to high school just at the time a handheld scientific calculator, wasn't even scientific, what we would call a four-function calculator now, was just invented. In my high school classroom, we all still use slide rules. Of course, this one, if you look at the console here, this is actually in Houston, Texas. It is part of the base of operations for NASA, which put us on the moon. This is Apollo 11. So logarithms, and through their application with the slide rule, allowed us to go to the moon. When you think about your T-83, 84, even a basic scientific calculator today, all the calculations you can do on those is enough to get you to the moon. So there's some pretty powerful things happening there. And some people, such as Gene Roddenberry, even imagine that deep in the far future when we're traveling at light speed, folks like our dearly beloved Mr. Spock would still be using slide rules. Even with all the little blinky lights and fancy computers they had for their time, our dear friend Mr. Spock is still using a slide rule. Some things never go out of style. I have a personal collection of them myself. So, what is a logarithm? Well, logarithms, if we take a basic exponential equation, okay, so some number raised to some exponent is equal to another number. Well, In logarithms, we redefine this and we write logarithm short for log, and we write base b, right, because we would call this the base of the power, base b, of a would be equal to c. Okay? These are identical ideas. They're just restating the problem in a different way. This one says, if I know the base and the exponent, what's a? This one says, if I know the base and the answer, what's the exponent? Okay? Now, the key idea here is that this is an exponent. Okay? Key idea. Notice the c is an exponent. Therefore, this whole log is the exponent. Okay? That's what all of this means. And we can actually use this, so let's take this idea. So we have b to the c. Okay, well, another way I could write that is b to the log base b of a. Well, we know the answer of that is just equal to a. Okay? And it's one of our fundamental identities when we're working with logarithms. Okay. Now, a couple of things we need to look at. Since we are dealing with a function, we need to talk about the domain of this. Okay. So here's the assumptions we're going to make. Okay. Assumptions are very key. They let us know where we're starting from. Okay. The first is that my base is greater than 0. Okay. So this number b has to be greater than 0. We're not going to allow negative numbers for the base. There's no such thing as a log base negative number. Okay? Also, if we think about a base being 0, 0 to any power except 0 is going to be 0. So, that really doesn't do too much for us. So, that's a key assumption. Well, if I have that, if b is greater than 0, then if I take a positive number to any exponent, okay, where c is greater than 0, okay, I know b is going, a is going to be greater than 0, right? So b to the first will be b to the second be b squared. Okay, all of that kind of makes sense. If I take b to 0, okay, we should remember from elementary algebra, that essentially means b divided by b, which is going to be 1. So anything to the 0 power is going to be equal to 1. And if we take that idea just a tiny bit further, if b has an exponent that's less than 0, essentially what this is meaning is 1 over b to the c, and once again that's going to be equal to a, and that's going to be greater than 0. So log base b of a, notice that a always has to be greater than 0. There's no way that I can take some number and put it to an exponent and end up with 0 as an answer. Try it all you want. You can get infinitely close. You can run it on your calculator. Eventually your calculator is going to get tired and round it off to 0, but all you're going to end up with essentially is something greater than 0. So a always has to be greater than 0. Okay? So the domain for this, okay, my a always has to be greater than 0. Notice a cannot be equal to 0 because there is no exponent I can put on a base that will give me 0 as an answer. Okay, moving on. Okay. Now then, so let's look at a little bit here. B to the c is equal to a. Okay, I know c is essentially any real number. Okay, I know a is always going to be a real number that is greater than or equal to 0. I'm sorry, greater than. I just told you one thing and then I try and lead you astray. So a is always going to have to be greater than 0, because b to the c is always going to have to be greater than 0. Now, take a pretty simple example here. We know 10 to the 0 equals 1, as we were just saying. We know 10 to the first is equal to 10. Okay? Logarithms give me an answer, 10 to some power. Could I have it be equal to 5? Is that possible? Well, let's write this in terms of logarithms. Log base 10 of 5 is equal to x. Now, if you put this into your calculator, what you will do is you will use the log button, and it depends on what kind of calculator you're using. If you're using something like a TI-8384, which is what you should be using in this class, you would push the log button, LOG, and then you would enter the number 5, and then you would push enter. And you will be given a decimal number. It's going to be between 0 and 1. That will give you the exponent that we need to put on 10 to get 5. Okay? This is perfectly legal because normally we are used to, dealing with exponents being integers. Okay? That's what we're used to seeing. But now what we're saying is exponents can be anything, okay, as long as it is a real number. So I can have 10 to the square root of 2. This is perfectly legal. It is going to give me a number that is less than 100 but more than 10, because I know the square root of 2 is approximately equal to 1.414. So that's going to give me an answer between 10 and 100. Do this on your calculator. Okay, go ahead and give it a shot. Type the number 10, then hit the little caret symbol. Okay, that means powers, and then do 1.414 and see what you end up with. Okay, it's going to be a real number. May not be a pretty number, but it's still going to be a real number that's between 10 and 100. Okay. So, with that basic introduction, we will let it go for now, and we'll get another video posted here that includes a couple of examples and take us a little further in how to use these. For the time being, I want you to play around with this on the calculator and kind of see what it looks like, get a feel for what's going on, and then we'll put a little more formality with it later. So thanks and good luck.